Welcome! In this session, we'll dive into an exciting problem, problem number 713, subarray product less than k. Together, we'll walk through the problem statement, explore the key challenges, and discuss efficient approaches to solve it. Let's get started. In this problem, you're tasked with finding the number of contiguous subarrays within a given array of integers, nums, where the product of all elements in the subarray is strictly less than a given value, k. A key point to note is that if k is less than or equal to 1, the result will always be 0 because no product can be strictly less than 1. The input includes the array nums and the integer k, with constraints ensuring the length of the array is between 1 and 30,000, and each element in nums is a positive integer between 1 and 1,000. The output will be an integer representing the total number of valid subarrays that meet this condition. To better understand the problem, let's look at an example. Suppose the input array is nums equals 10, 5, 2, 6, and k equals 100. Here, there are 8 subarrays whose product is strictly less than 100. For instance, the subarrays 10, 5, 2, and 6 each have a single element, and their products are 10, 5, 2, and 6, respectively, all of which are valid. Similarly, subarrays like 10, 5, 5, 2, 2, 6, and 5, 2, 6 have products of 50, 10, 12, and 60, which are also valid. However, larger subarrays like 10, 5, 2 exceed the product limit, so they are invalid. The total count of valid subarrays, therefore, is 8. Let's consider a few more examples. In the second example, with nums equals 1, 2, 3, and k equals 0, no product can be strictly less than 0, so the result is 0. In the third example, with nums equals 1, 1, 1, and k equals 2, every subarray is valid because all products equal 1, which is less than 2. For example, there are 3 subarrays consisting of a single element, 1, 2 subarrays of 2 elements, 1, 1, and 1 subarray, 1, 1, 1, containing all 3 elements. Adding these up, the total count of valid subarrays is 6. These examples demonstrate how the problem handles different input scenarios, from cases where no subarray is valid to cases where every subarray satisfies the condition. Now, let's discuss the constraints and edge cases to consider. The array's length can be as large as 30,000, so any solution must be efficient to handle this upper limit. Additionally, the value of nums, I, can be as large as 1,000, so the algorithm must ensure that calculations do not lead to overflow. If k is 0 or 1, the output is always 0 because no product can be strictly less than these values. For small arrays with 1 or 2 elements, the solution must handle them correctly. Similarly, when k is small but the array is large, the solution must perform efficiently without exceeding time limits. Cases where all elements in the array are the same or where all subarrays are valid should also be tested. The output, in all cases, is an integer representing the total number of valid contiguous subarrays. To solve the problem of finding the number of contiguous subarrays where the product of all elements is strictly less than k, we can consider 2 main approaches, a brute force method and an optimized technique. First, let's explore the brute force approach. The intuition here is straightforward. We generate all possible subarrays, calculate their product, and check if the product is less than k. The steps involve iterating through all possible starting indices, and for each starting index, we compute the product of all subsequent elements until either the product exceeds k or we reach the end of the array. Finally, we count the number of valid subarrays. However, this method has significant drawbacks. Its time complexity is n squared, since we are generating all subarrays and calculating their product, and while the space complexity is 1, the brute force approach becomes impractical for larger arrays due to its inefficiency. Now, to address the inefficiency of the brute force method, we turn to the optimized sliding window technique, which leverages a running product to dynamically maintain a window of valid elements. Instead of recalculating the product for every subarray, this approach allows us to adjust the window as we process the array. The steps are as follows. We use 2 pointers, start and end, to represent the window. As we expand the window by moving end and including the current element in the product, we check if the product becomes greater than or equal to k. If it does, we shrink the window by moving start until the product is valid again. A key observation here is that the number of valid subarrays ending at end is equal to end start plus 1, because all subarrays within this window have products less than k. This approach significantly reduces the computation time, with an overall time complexity of O(n), since each element is processed at most twice, and a space complexity of O(1), as we use no additional data structures. The breakthrough insight here is that by maintaining a running product and dynamically adjusting the window, we can avoid recalculating the product for every subarray, saving substantial computation time. This realization forms the basis of the sliding window approach. Comparing the two strategies, brute force is easier to understand and implement but becomes inefficient for larger inputs due to its O(n)² complexity. On the other hand, the sliding window technique is both time efficient and space efficient, making it the clear choice for larger datasets. While alternative methods like binary search might work in some scenarios, they are not applicable here due to the unsorted nature of the array and the dynamic constraints of the problem. Ultimately, we choose the sliding window approach as the optimal solution because it balances simplicity, efficiency, and clarity. This makes it an excellent choice for competitive programming and real-world applications where performance is crucial. The goal of this problem is to count all contiguous subarrays where the product of the elements in the subarray is strictly less than a given integer, k. We are given an array of positive integers, nums, and an integer k as inputs. To solve this problem efficiently, we use a sliding window approach. This method allows us to dynamically adjust the size of a window to include or exclude elements based on the product condition. To begin, we initialize three variables: left, which marks the start of the window, product, set to 1, which keeps track of the product of elements within the window, and count, initialized to 0, to store the total number of valid subarrays. These variables set the foundation for iterating through the array and finding the solution efficiently. To implement the sliding window approach, we begin iterating over the array. For each element, we use a variable right to expand the window by including the current element in our product calculation. If at any point the product becomes greater than or equal to k, we adjust the window by shrinking it from the left. This is done by dividing the product by nums, left, and then incrementing the left pointer, which effectively excludes the leftmost element from the window. Once the product meets the condition of being less than k, we calculate the number of valid subarrays ending at the current index. These subarrays start from the left pointer and extend to right, and their count is simply right left plus 1. By adding this to our total count, we ensure all valid subarrays for the current right are accounted for. Finally, after completing the loop, we return the total count of valid subarrays. Let's go through a concrete example to see the algorithm in action. Consider the input array nums equals 10, 5, 2, 6, and k equals 100. We start by initializing left to 0, product to 1, and count to 0. Now, as we iterate, when right is 0, the current element is 10. Multiplying 10 into the product gives 10, which is less than k, so we count the single subarray, 10, adding 1 to count. Moving to right equals 1, the current element is 5. The product becomes 50, which is still less than k, so we count two subarrays, 10, 5, and 5, adding 2 to count, making it 3. At right equals 2, the current element is 2. The product becomes 100, which is not less than k, so we adjust the window by dividing the product by nums, left, which is 10, and increment left to 1. This updates the product to 10, and now we count the valid subarrays, 5, 2, and 2, adding 2 to count to make it 5. Continuing with the example, we now move to right equals 3, where the current element is 6. Including 6 in the product results in 60, which is less than k. Thus, we count all subarrays ending at this index, 5, 2, 6, 2, 6, and 6, adding 3 to count to reach a total of 8. Having processed all elements in the array, we return the final count, which is 8. This means there are 8 subarrays in nums where the product of all elements is strictly less than k. This algorithm is efficient due to the sliding window technique. Instead of recalculating the product for every possible subarray, we maintain a dynamic window that adjusts as needed. The sliding window ensures that the product stays valid while minimizing unnecessary computations. For each position of right, we instantly know that all subarrays starting from left to right are valid, which simplifies the counting process. Additionally, shrinking the window dynamically ensures that we only process each element a limited number of times. It's important to consider edge cases. If all elements are greater than or equal to k, the result is 0 since no valid subarrays exist. Similarly, when k is 1 or less, the result is also 0, as the product of positive integers will always be at least 1. To implement this algorithm, we primarily rely on a sliding window represented by two pointers, left and right. These pointers define the boundaries of the current window. We also use a few variables, product to maintain the product of elements within the window and count to keep track of the total number of valid subarrays. The algorithm's efficiency lies in its time complexity of O(n). Each element in the array is processed at most twice, once when added to the window and possibly once when removed. The space complexity is O(1), since no additional data structures are required, and only a few integer variables are used. This makes the approach not only efficient but also memory-friendly, which is ideal for large input sizes. This code efficiently solves the problem using the sliding window technique. The function begins by checking if k is less than or equal to 1. In such cases, it's impossible to have a valid subarray, so we return 0 immediately. The product variable keeps track of the product of the current window. We also initialize count to store the total number of valid subarrays and start to represent the beginning of the sliding window. We then iterate through the array using the end pointer. For each element, we multiply it into the product. If the product exceeds or equals k, we shrink the window by dividing the product by nums, start, and incrementing start until the product becomes valid, less than k. For every valid window, the number of valid subarrays ending at the current end is given by end start plus 1. We add this value to count. The algorithm ensures efficiency with a time complexity of O(n), as each element is processed at most twice, once when expanding the window and once when contracting it. This makes it suitable for large inputs. The solution handles edge cases like an empty array or k too small gracefully. The overall implementation is compact and adheres to the sliding window paradigm effectively. This is the Java implementation of LeetCode problem number 713, subarray product less than k. The logic mirrors the Python solution, using a sliding window to efficiently calculate the number of subarrays where the product is less than k. Key differences include type declarations for variables and the absence of Python-specific features like integer division, //. The for loop iterates through the array, and the while loop ensures the product remains less than k by shrinking the window from the left. This approach maintains an O(n) time complexity. In this problem, we are tasked with finding the number of contiguous subarrays within an array where the product of all elements in each subarray is strictly less than a given value, k. To solve this efficiently, we use a sliding window technique, also known as the two-pointer method. Let's walk through an example where nums is 10, 5, 2, 6, and k is 100. We start by initializing three variables, product to 1, count to 0, and start to 0, which marks the beginning of our window. Initially, with end at index 0, we multiply the product by nums, end, which is 10. Since the product is less than k, we calculate the number of subarrays ending at this position, which is determined by end start plus 1. This gives us one subarray, 10, so we add 1 to the count. Next, we move into index 1. The product becomes 50 after multiplying by nums, end. Again, it's less than k, so we calculate all subarrays ending at this index, adding 2 more subarrays, 5, and 10, 5. The count is updated to 3. Moving end forward to index 2, the product becomes 100 after multiplying by nums, end. Here, the product is not less than k, so we adjust the window by dividing the product by nums, start, and incrementing start. This reduces the product to 10, which is now less than k, allowing us to count 2 subarrays, 2, and 5, 2. The count is updated to 5. Now, as we move into index 3, we multiply the product by nums, end, which is 6, resulting in a product of 60. Since this is still less than k, we calculate the number of subarrays ending at this position. These include 6, 2, 6, and 5, 2, 6, adding 3 more to our total. The count is updated to 8. At this point, we've processed all elements in nums, so the final output for this example is 8. Let's consider another case where nums is 1, 2, 3, and k is 0. Here, we initialize the same variables as before, but since k is less than or equal to 1, no subarray can meet the condition. Therefore, we immediately return 0 as the result, without any further calculations. Let's examine a third example with nums as 1, 2, 3, and k is 2. After initializing product, count, and start, we begin with end at index 0. Multiplying product by nums end gives 1, which is less than k, so we count the subarray 1, adding 1 to count. Next, we move end to index 1, making the product 2 after multiplying by nums end. Since the product is now equal to k, we adjust the window by dividing the product by nums, start, and incrementing start. This reduces the product to 2, and we divide again because the product is still not less than k. After dividing by nums, start, again, the product becomes 1 and start is increment to 2. At this point, we count the subarray 2, adding another 1 to count for a total of 2. Finally, we move end to index 2. Multiplying product by nums end gives 3, which is greater than or equal to k. We adjust the window by dividing the product by nums, start, and incrementing start to 3. Now start is greater than end, so no subarrays are added. The final output for this example is 2. From these examples, several key observations emerge. First, the sliding window technique helps us dynamically adjust the start of the window whenever the product becomes greater than or equal to k. At each step, the number of new subarrays introduced is calculated as end start plus 1, allowing us to efficiently count subarrays without explicitly generating them. This approach ensures that each element in the array is processed at most twice, leading to an overall time complexity of O(n). This efficiency makes the sliding window method an ideal choice for solving this problem. The time complexity of this solution is O(n), where n is the length of the input array. To understand why, consider how the two pointers, end and start, operate. The end pointer iterates through the array, and this outer loop executes exactly n times. Inside the loop, the start pointer adjusts to ensure that the product of the current subarray remains less than k. The key observation here is that each element is only processed once by the start pointer. This is because once an element is removed from the product, it is never reconsidered. Overall, the combined movements of both start and end pointers are at most 2n operations, each moving from index 0 to n at most once. Consequently, the total time complexity is O(n). The space complexity of this solution is O(1). This efficiency comes from the fact that the algorithm only uses a few integer variables, such as product, count, start, and end, for tracking the state of the computation. These variables require a constant amount of space, regardless of the size of the input array. Additionally, no auxiliary data structures, such as arrays or hash maps, are used. The algorithm operates entirely in place, meaning it doesn't depend on any extra memory for intermediate storage. As a result, the space complexity remains constant at O(1). Let's compare this optimized approach to a brute force solution. A naive approach would involve generating all possible subarrays of the input array and checking whether the product of each subarray is less than k. For an array of size n, there are O(n²) subarrays, and calculating the product of each subarray can take up to O(n) time in the worst case. This would result in a total time complexity of O(n³). By contrast, the sliding window approach drastically reduces this overhead. Instead of recalculating the product for every subarray, it updates the product incrementally as the window expands or shrinks. This eliminates the need to check each subarray individually, reducing the time complexity to O(n). This optimization is a significant improvement over the brute force approach, making the algorithm much more efficient. The efficiency of the sliding window approach is evident when analyzing the best, average, and worst case scenarios. In the best case, if all elements in the array are less than k, the start pointer doesn't need to move, and the algorithm runs in O(n). On average, the start pointer moves a few times for each increment of the end pointer, but the overall complexity still remains O(n). Even in the worst case, where all elements in the array are very large compared to k, the start pointer may move for every increment of end. However, since each pointer processes each element at most once, the total operations are still bounded by 2n, ensuring a time complexity of O(n). From a mathematical perspective, each increment of end and start takes constant time, and their combined movements are limited to 2n. This sliding window approach not only brings the time complexity down from O(n³ to O(n), but it also maintains a constant space complexity of O(1), making it an optimal solution for handling large input sizes efficiently. When tackling this problem, one common mistake is relying on brute force to calculate the product for all possible subarrays. This approach typically has a time complexity of O(n) cubed, or O(n) squared, which becomes infeasible for larger arrays due to time limits. To address this, we can optimize the solution using a sliding window or two-pointer technique, which brings the complexity down to O(n). Another issue to watch out for is when the value of k is very small, specifically when k is less than or equal to 1. In such cases, no subarray will satisfy the condition of having a product less than k, and neglecting to handle this scenario may lead to incorrect results or even runtime errors like division by zero. Lastly, overflow errors can occur when calculating the product of large numbers, especially with larger input sizes. A good way to prevent this is by using division or logarithmic transformations to manage the product calculations more efficiently. Another challenge arises with the sliding window technique, where incorrect movement of the start pointer can lead to errors. For instance, failing to properly adjust the start pointer to maintain a valid product can result in counting incorrect subarrays. It's essential to carefully manage the window so that the product remains valid throughout the process. Additionally, off-by-one errors are a frequent pitfall, especially when counting subarrays. To account for all valid subarrays within the current window, the formula and start plus 1 should be used. This ensures that the count reflects the correct number of subarrays for the given window size. Testing this logic with small cases can help solidify your implementation and avoid subtle errors. This problem is a great example of the two-pointer technique, which is commonly tested in interviews. Interviewers often look for your ability to explain how the sliding window expands and contracts based on the conditions. It's also important to discuss the trade-offs between brute force and optimized solutions. While brute force might be easier to implement, it's inefficient, and the sliding window approach, though more complex, offers significant performance improvements. Furthermore, handling edge cases such as zeros in the array or very small k values demonstrates your adaptability to unexpected constraints. During interviews, it's helpful to articulate your thought process clearly, starting with the brute force approach to identify inefficiencies and then transitioning to the optimized solution. For additional practice, exploring related problems like LeetCode 209, 438, or 424 can deepen your understanding of sliding window techniques and their variations. There are several approaches to solving this problem, each with its own trade-offs. The brute force method, with a complexity of O(n) cubed, or O(n) squared, depending on the implementation, is straightforward to understand but impractical for large inputs due to its inefficiency. A more optimal approach is the sliding window or two-pointer technique, which has a time complexity of O(n). This method is highly efficient but requires careful attention to implementation details to avoid mistakes. Another alternative is using logarithmic transformations, where multiplication is replaced with addition by applying logarithmic properties. This can help prevent overflow issues when dealing with very large products. However, this approach adds complexity to the solution and may be harder to explain in an interview setting. Understanding these different strategies and their trade-offs allows you to select the best approach for the given problem constraints. Great job! To wrap up, we reviewed the key ideas and strategies for solving this problem. Sliding window techniques are an excellent tool for optimizing subarray problems, and we hope this session gave you clarity and confidence. Thanks for tuning in. Be sure to subscribe for more problem-solving walkthroughs. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!